Let me ask you two questions. Let's say we have a sprinkler and this is a top view of the sprinkler and it's shaped in such a way that water is exiting from one side in this direction and from the other side in this direction. It's a top view and it's hinged at the center. Now, all of you have seen this before and you can intuitively figure out that when this happens, the sprinkler will rotate, right? And it will rotate in the clockwise direction when water is flowing out from both the ends. Now, there is this other problem which is referred to as Feynman sprinkler, which is the opposite of this. Now, what if this whole sprinkler was inside a water bath and the sprinkler was sucking in water? So, instead of water exiting here, it is entering from here and going inside, and likewise from here. The question is, will the sprinkler still rotate? And if it rotates, will it rotate clockwise or will it rotate counterclockwise? Now, I really enjoyed reading this book. Surely you're joking, Mr. Feynman, and I do recommend if you guys can get a hold of that book. A lot of such interesting ideas are discussed in that book, and a lot of pranks that Feynman as a graduate student did at his school, at MIT, at Caltech, bunch of places. It's a very interesting book. Okay, this is first question. You can try this at home. You can set up an experiment and try that at home. Now, let me ask you a second question. What if you have a simple incline followed by a level ground and you have a disk that you let go from a certain height edge, and then it rolls down the incline, rolls without slipping, and it attains a certain velocity when it reaches the level ground. Now, instead of the disk, if you had a ring of that same mass and you let it go from the same height, the question is, will it have a different velocity when it reaches here? If so, then why? Right? So, this is again an experiment that you can set up at home and you can try. But let's try to see if we can develop some kinematics principles that you can apply to these situations to answer them. So, welcome to this concept refresher capsule on kinematics. Again, a few disclaimers. We don't really go through rigorous derivation here, but just show you the spirit of the derivation. You really have to spend time with these derivations on your own to master them. But more importantly, you have to really develop experience by applying these in many different situations, in many different problems. Practice is central for you to gain mastery over these very simple principles. Right? So, don't be under a false sense of security that you understood these problems. You really have to master them by applying them over. And with that, let's go back to kinetics. Let's start with Newton's law that everybody is familiar with. Here, notice they are vectors, and when I write F here, I really mean the total resultant force acting on the particle. We are at the moment only talking about a single particle. The total net resultant force on the particle is equal to mass times acceleration of the particle. Vector equation that can be resolved in any set of coordinate frames as per convenience. The only assumption here is really that when you are doing the calculus, when you are doing the derivative to find the acceleration, you are doing that relative to an inertially fixed frame. Otherwise, this is universally applicable. All right, now let's look at a system of particles. Now, let us imagine there are n particles. All these blue points are particles. Each one has a mass, m1, m2, mi, mj. So, let's talk about two general particles, I and j, and totally there are n of these. Now, the total external force, the resultant external force acting on particle 1, I am calling F1. Again, remember there could be multiple forces acting on M1, but the resultant of all of that is what I am calling F1. Likewise, on each of these you could have external forces. So, on ith particle, let us say the total external force is Fi, and jth particle it is Fj. But you can also have forces of interaction between these particles. So, little Fij is the force on particle I due to particle j, and likewise little Fji is the force on particle j due to particle I. And as you can immediately guess, these will always be equal and opposite because they are forces exerted on each other, and there will be combination of these with all of the n particles. Now, there is no assumption that these particles are connected in any way. They may or may not be interacting, they may or may not be connected, they may be connected with rigid link, they may be connected with the spring, with the string, it does not matter. This is a very general setting. Now, let us imagine origin is at O, position vector of ith particle is Ri, position vector of jth particle is Rj. Here, let us write the same Newton's law for the ith particle. So, if we do that, for the ith particle, we get Fi plus sum over j other particles Fij is equal to mass of the ith particle times acceleration of the ith particle. Now, if we sum over I particles, I get sum over I Fi plus I get a double sum Ij of Fij, and on the right hand side I get sum over I MiAi. Because these internal forces occur in equal and opposite pairs, you can see right away that this double sum is 0. On the right hand side of that equation, let us go over here, and we are familiar with the definition of center of gravity is really sum of MI divided by sum of MI, and this let me just call M. Therefore, sum of MI is equal to just MRG. Now, if I differentiate this twice, the same sort of expression I get for acceleration as well. Now, I can go back to this picture, I can draw a center of gravity . Some people like to use the special symbol for center of gravity, so let me use that. And the position vector of this center of gravity is Rg. Okay, now if we come back to our system of particles expression here again, we get something much simpler. We can erase this and the whole thing becomes the sum of all external forces acting on the system of particles is equal to just the total mass of the system of particles times the acceleration of the center of gravity. So, this is always applicable and this all follows from Newton's second law. So, Newton, of course, everybody knows about Newton. There are lots of interesting stories about Newton. For instance, during the Great Plague, he spent time at home. He was a young student at that time, and he developed much of calculus and laws of motion during that time as well. But there are also some very interesting comments about his social life. So, for instance, one French writer wrote about him, he was never sensible to any passion, was not subject to the common frailties of mankind, nor had any commerce with women. So, Newton is Newton. Okay, now let's go back to Newton's law for a particle. Now, if we multiply by dt on both sides and integrate over a period of time, we get integral f dt going from time instant t1 to t2 is equal to integral ma dt t1 to t2. Now, the term on the left hand side is called the impulse in going from time instant 1 to time instant 2, and this is dv by dt, and dt cancels. So, integral of dv simply gives me mv. So, this becomes mv at time t2 minus mv at time t1. So, this gives rise to the impulse momentum principle. The total impulse acting on a particle is equal to the change in momentum of that particle. Couple of observations here. Remember, these are all vectors. The impulse is a vector because for f times dt still gives you a vector. Also, sometimes you may know the force profile and you may have a finite time interval and you can compute this by doing the integration. Sometimes you may be dealing with a situation where you have a really large force for an infinitesimal time period. So, it is very hard to compute this, but still the effect of that entire impulse can still be seen in the change in momentum. So, when Dhoni hits a 6, ball comes and hits the bat, it is a very small time duration for which contact is maintained, but you can see the change in momentum of the ball, and from that you can compute what is the impulse applied by the bat on the ball. Now, I can take the same approach again to our system of particles. So, I can go back and write Fi plus sum over j Fij is equal to miai. Again, I do integral dt on both sides, and then I sum over I particles. Then I would get the total impulse in going from time 1 to time 2 only due to external forces. Because of the double summation, again your Fij times dt will cancel out. The fact that it is multiplied by dt does not change that fact because it is just a scalar multiplication. You will still have that, and that does not depend on I. And again on the right hand side you will get a summation over I integral miai dt, and the same thing applies, but now you have a summation. So, you would have a mi vi summation over I. So, that would again give me the total mass times velocity of center of gravity, but again time t2 minus time t1. So, the same thing is applicable to a system of particles, but now the momentum that I am talking about is of the center of gravity. We can now start talking about rigid bodies, and everything that we have done here is still applicable to rigid bodies as well. Of course, instead of doing a sum over I, when we are talking about rigid body, instead of mi, you might have a dm, you might have an infinitesimal element, and instead of summing over I, you may be integrating over dm. So, the operation will change, but the principle will remain the same, and you will still get something, you will still get exactly the same thing. The total impulse due to external forces acting on the rigid body from time instant 1 to 2 is equal to the change in momentum of the center of gravity of the rigid body. Now, this principle also helps you go back to Feynman's sprinkler and try to see if you can answer that question. because you can look at the change in impulse of the water that is exiting or entering, depending on which one you are talking about. And from that you can figure out what is the impulse applied onto the water, and there is an equal and opposite impulse that is applied by the water onto the sprinkler, and then you can see what sort of motion that causes. You can even apply this to, as I said, system of particles where, sometimes, so let's talk about Gravity, the movie. That's another fantastic movie that I would recommend that you guys watch. A lot of dynamics principles involved. So when two astronauts are floating around in space with a tether in between, sometimes the tether is taut, sometimes it is loose, but this will still be applicable. If there are no external forces acting on both the astronauts, their center of gravity then will have the same consistent momentum. So you can apply this in many different principles, many different situations. Sorry. Okay, now let's go back to a different principle, that was impulse momentum, where we essentially took Newton's law, multiplied by dt on both sides and integrated. But now let's dot product both sides with dr and then integrate from configuration A to configuration B. Now these are not points A and B, this is a configuration. Now here dr is a vector, so we really have to talk about a dot product, and when we have a dot product, remember this is a scalar. Unlike impulse momentum where both sides of the equation you had vectors, now you will have scalars. Now if we do this, we get f dot dr A to B is equal to A to B ma dot dr. Just a quick note on this, B dot dV I can write as dr by dt dot with dV. I can take dt here. This is, as I said, a crude derivation, just to give you the spirit of how these things are derived, and this becomes just dr dot with A. So this dot product can be written as V dot dV. Now this leads to an expression which some may find surprising. This is trivial, but still many students I find have forgotten about this, that the total work done due to external forces in going from A to B is not equal to the change in total energy, but really only the change in kinetic energy. This gives me half m V dot V, and that to at B minus half m V dot V at A. So this is the difference in kinetic energies. So let me write this again. So the total work done by external forces, let me call it U, because W we tend to use for weight, so I don't want to use W, in going from A to B is equal to the kinetic energy in configuration B minus kinetic energy in configuration A, where T is half m V squared. So now this may lead you to question what happened to potential energy. Now that's a different discussion. I like to joke with my students that I consider potential energy to be a fake energy, because depending on where your datum is, you can have negative potential energy, right? So how can an energy be negative? So there must be something wrong with potential energy. But anyway, the truth of the matter is potential energy is nothing but a pre-packaging of work done, and really you can write work done as a sum of two terms, work done by conservative forces in going from A to B plus work done by non-conservative forces in going from A to B. And non-conservative forces are forces that the work done by them depends on the path taken, whereas conservative forces are the forces for which the work done by them is independent of the path taken and only depends on the end points. So therefore, when you're talking about work done by conservative forces, you can pre-package them, write them in standard expressions that you can use readily without having to worry about the path taken in going from A to B. And that is what typically you pre-package as potential energy. So potential energy, another way of thinking about it is it's work done by certain forces which the work done only depends on the endpoints, and therefore you can derive expression ahead of time and use them and call them potential energy. But if you look at the basic derivation, you only get kinetic energy here. That is one thing to keep in mind. So this was for a single particle. Now we can go back to a system of particles. Let's come over here. Again, let's think about the ith particle. Again, let's write a similar expression that we had written earlier. But now let's be a little bit more careful about these forces and work done by these forces, because you will notice that in work energy principle, it gets a little bit more complicated. Fi plus sum over j Fij is equal to MIAI. Now let me dot with DRI on both sides. And then integrate, going from configuration A to B. So now if we sum over I particles on both sides, so on the left hand side I get sum over I A to B Fi plus sum j Fij dot with Dri, and on the right hand side I get sum over I, but again I can write this as Vi dot with dVi. Again, right hand side looks like some sort of kinetic energy, but on the left hand side, one interesting thing is now this double sum of internal forces doesn't necessarily add up to 0, because each of those internal forces is now dot with a different Dri. So just to give you an example, supposing there were two particles connected by a spring and they were both extending, even though the forces are equal and opposite, which are, if there's extension in the spring, there are forces pulling them closer to each other. But in each case, the particle is moving in the opposite direction of the force, so negative work here and negative work here. So it doesn't cancel out, it becomes double negative, right? So you can see that this sum no longer adds up to 0. So it's a little bit more complicated to work this out for a system of particles. You will see that you get work done due to external forces and you get work done due to internal forces. And on the right hand side, again, you can split this in a bunch of terms. This is a standard trick that we would use for both this and other principles later on, where for each I, now I write Ri, which is this position vector, as a sum of two position vectors, Rg plus Rig. So Ri is equal to Rg plus Rig, and I can do that for velocities as well. So let's move on beyond system of particles. What is even more interesting, system of particles for work energy has a few terms, but let's talk about rigid bodies. Now in rigid bodies, something special happens. In rigid bodies, you can no longer have this kind of situation where two particles are moving away from each other or close to each other. The distance between them is fixed. So if there are equal and opposite internal forces acting on two differential elements, then when I do the dot product with drs, even though they may have different displacements, but the work done by both of them will be equal and opposite. So that will still cancel out. So when I am talking about a rigid body, without going into the details of the derivation, you can intuitively see right away that this becomes total work done going from A to B only due to external forces. Now one thing to keep in mind here is, even though we say total work done by external forces, each force could have gone through a different displacement. So each force is dot with a different displacement vector. So if it's on a rigid body, if it's a reaction force and that is not moving through any displacement, then obviously that work done is 0. Whereas, at the other end of the rigid body, there's another force which is moving through a certain displacement, you would get a different dot product, dot with a different displacement there. So that's something to keep in mind. Each force is dotted with a different displacement. And on the right hand side, you would get sum of Mi Vi dot with Vi. Again, for simplicity, I am writing it as a sum, but as I mentioned earlier, for a rigid body, it's really an integral over dm. That's the right way to do it, but for simplicity, just to see how the spirit of the derivation works, so I'm using a summation here. And this, using the trick that I just mentioned earlier, I would write it as Mi Vg plus Vi with respect to G dot with Vg plus Vi with respect to G. So this obviously gives me 3 terms because this is like a square term. So I get Vg dot with Vg plus 2 Vg dot with Vig plus Vig dot with Vig. Sum over I Mi this, oh sorry, I am missing a half. This becomes half m Vg squared, the first term, plus the second term. If you will notice, this Vg is independent of the summation. So I can really do sum over I Mi Vi with respect to G. So I can write, I can write this as half times 2 times Vg dot with sum over I Mi Vig. And this, you can see, since this is all relative to the center of gravity, and this will be the in the end total mass times the velocity of center of gravity relative to center of gravity. So this will end up becoming 0, and I will get the third term, which is half Now there is something very interesting that happens here. The first term is the linear kinetic energy of the center of gravity. We already started with the assumption that it's a rigid body, and as I said, this is really an integral dm. But if you think about the velocity of a differential element I relative to the center of gravity in a rigid body, again remember the distances between the points are not changing. So, what we said in the previous concept capsule is that 2 points with fixed distance in between them, the velocity is just omega cross Rij. So, I can rewrite this as omega cross Rij dot with omega cross Rij. So, now you can see the genesis of where moment of inertia comes from. It is really an integral dm r squared. So, this term becomes a half I omega squared, but really since everything is a vector, I really have to write it as omega transpose I omega. And notice here that these are all position vectors relative to center of gravity. So, it is really moment of inertia about its center of gravity. So, let me write the whole thing again. For a rigid body, the total work done by external forces in going from configuration A to configuration B is equal to the change in kinetic energy. But now the kinetic energy has two terms. The first is the total mass times the velocity of center of gravity squared, plus the second term is the rotational kinetic energy, where I get half I omega squared essentially, but I really have to write it in a vector form. And this is moment of inertia about the center of gravity. This is a tensor. We haven't talked about it yet. We will talk about it later in one of the subsequent concept capsules. But what is also interesting is this whole moment of inertia came out of the derivation. And Euler first coined this term moment of inertia, and Euler is again one of the greatest mathematicians of all times. Lot of interesting stories about Euler. For instance, when this is not a story about Euler. When I look up the most common picture of Euler, it somehow reminds me of Russell Crowe. You might go and check it out. But he was initially actually at least his father wanted him to be a priest, and many of you may know already that he worked with Bernoulli. Bernoulli was his PhD advisor, in fact, and then Bernoulli convinced his father, Euler's father, that he has a lot of potential in mathematics, and then he should really pursue a career in mathematics and academia and not be a pastor. Of course, Bernoulli, again, many of you are familiar, but there are three different Bernoullis. I don't know how much you are all aware, but there's a father Bernoulli, and then there are two sons. All three of them have done excellent work, but I'm really talking about the father Bernoulli here. Now, Euler was also, he also went blind towards the end of his career. In fact, I think around 31, 32 years, in his middle ages, he lost sight in one of his eyes, and you can read about it. There's plenty of information online. And then towards the later half of his career, when he was 59 years old, he lost his second eye also because he had a cataract, and then the cataract surgery didn't go well. But if you look at when he coined the term moment of inertia, it was, if I remember correctly, just 1 year before he lost sight in his second eye as well. So that was just in the nick of time. But then interestingly, even after he lost his sight, he was prolific. I think he has developed so much theory that people are still figuring out, people are still publishing. So you might want to read about Euler. Okay, so that gives us the gyan of the day, that if others around you are asking you to be a priest, then maybe you shouldn't be a priest. maybe you are better off being a mathematician. Anyway, so let me end this session with reiterating that you can learn anything you want on your own with whatever limited resources you have. You only need patience and commitment.